Hi, everyone. Welcome to the webinar organized by Digito Technologies and qBraid on qubit encoding for secure communication. So with us, we have Govardhani, our quantum solutions engineer, along with Prajwal and Chiranjeevi, our solution engineers. Thank you for joining us today. And I'd like to begin by introducing our company. So Digito Technologies started in the year 2018, and for the last 8 years, we've been in the business working with both academia as well as research organizations. And we work across embedded systems, artificial intelligence, Internet of Things, edge intelligence, FPGA platforms, and test and measurement technologies with our partners. And we specialize in wireless technology, RF, 5G, 6G teaching and research solutions, and now quantum computing, quantum communication along with our partners. All right, so we work with our partner companies, ST Microelectronics, mostly on embedded platforms. With Digilant, we work across wireless systems as well as test and measurement equipments. With TMY Tech and Mantis, we work across wireless solutions. And Crobot Tech, we work with their robotic solutions. So on quantum communication and computing, we work with QU tools and qBraid. And we also have Amona teams we work with across signal processing platforms. All right. I would like to hand over the session to Govardhani, our solution engineer, to take the session forward. Now, we'll also have a dedicated Q&A session. We have set aside the last 10 minutes to answer your questions and to chat about any questions that you may have. Feel free to use that Q&A section to answer any of your questions. Over to you, Govardhani.
Yeah, thank you, Anu, for the initial convo. So I hope my video is also visible and screen sharing is also correct. Anu, I think you are muted.
Yes, Govardhani, we are good to go.
Yeah, sure. So hello everyone, good afternoon. So welcome to this session on Qubit encoding for secure communication. So in this webinar, we are going to explore one of the most fascinating concepts in quantum communication, like how a single qubit can be used to represent and transfer more information than a classical bit. Okay. So before we begin, a quick introduction about myself. I'm Govardhani, working as a solution engineer at Digito Technologies, and my area of focus mainly is quantum computing and quantum cryptography, as well as qBraid-based quantum developments and cloud-connected intelligence systems. So today's session mainly focuses on understanding how quantum communication works and how qubits can be used for secure information transfer. And the core part of the webinar will be like understanding the workflow of quantum cryptography, and you will also learn how information is encoded into the qubits, and you will also see a quick demonstration on the superdense coding. Okay, so for the participants who are new to this series or may have missed our previous webinar, the complete recording is available through this link, and that session covers the fundamental concepts of quantum computing, includes qubits, quantum gates, and basic circuit executing using the qBraid. Okay, so it can serve as a helpful foundation for understanding today's topic on quantum communication and secure information coding. So, to understand the quantum cryptography properly, we first need to compare it with how security works in classical systems, right? So, in classical cryptography, information is secured using mathematical encryption algorithms, right? The original data is converted into an encoded format using a key and specific mathematical operations, right? And only someone who possesses the correct decryption key can convert that encrypted data back into the readable information. The important point here is that classical cryptography mainly depends on computational difficulty. Okay, the security is based on the assumption that solving certain mathematical problems would take an extremely long time using the classical computers. For example, factoring very large numbers or discrete logarithmic problems and complex key generation mechanisms, right? So the protection comes from the idea that breaking the encryption is computationally impractical. Now, quantum cryptography works very differently. So instead of depending only on the mathematical complexity, it uses the actual law of quantum mechanics to secure the communication. And here, the security mechanism is directly converted to the behavior of quantum states themselves. And one of the most important principle is that quantum information cannot be observed without disturbing it. And this happens because quantum states exist probabilistically before measurement, right? The moment someone tries to intercept or measure the transmitted qubit, the quantum state changes or collapses into a classical bit. So that disturbance immediately introduces detectable changes in the communication process. So unlike classical systems where interception may remain invisible, or quantum cryptography can reveal the presence of an eavesdropper itself. So this is what makes quantum cryptography fundamentally different. Okay, so the system is not encrypting information but also physically detecting unauthorized observation through the quantum behavior. And another major advantage is that quantum communication also supports phenomena like entanglement and superposition, which enables advanced communication protocols that are impossible in purely classical systems. Okay, so to understand how secure quantum communication actually happens, we need to understand the major components involved in the quantum cryptographic system. And a communication system is not built using a single technology alone. It combines quantum information processing as well as transmission systems, measurement mechanisms, and classical coordination networks together. So the first and most important component is the qubits, that are the fundamental carriers of the quantum information. Unlike classical bits that can exist only as either 0 or 1, right? But qubits can exist in superposition, meaning they can represent multiple probability states simultaneously. Because of this property, qubits become capable of carrying and processing the information in a completely different way from a classical systems. And the second component is quantum gates. And quantum gates are operation used to manipulate the qubit states. Okay, so these gates control how information is encoded into qubits. For example, some gates create superposition and some flip quantum states, right? And while others create entanglement between the multiple qubits. Without quantum gates, the qubits would simply remain in their initial states and no meaningful communication or encoding could happen. And the next important component is the measurement system. So the quantum systems behave differently before and after the observation. And before measurement, a qubit exists probabilistically, but during the measurement, the quantum state will collapse into a definite classical outcome. So the measurement systems are therefore responsible for converting the quantum information into readable classical information at the receiver side. Okay, and another major component is the quantum channel. And quantum channel are the communication pathways through which qubits travel between the communicating parties, that are receiver as well as sender. And these channels may use optical fibers or free space optical communications and satellite based links or dedicated quantum communication infrastructure. So the important requirement is that the channel must preserve fragile quantum properties like superposition and entanglement during the transmission. Okay, and finally we also need a classical communication network, right? So this is because not every operations in quantum cryptography can be handled purely through the quantum states. So classical channels are still required for synchronization, verifications, as well as basis comparisons and error checking, as well as eavesdrop validations. So, in reality, quantum cryptography is not replacing classical communication completely. Instead, it combines quantum communication and classical coordination together to achieve secure information exchange. Okay, so let's get deeper into each components. Firstly, we have the qubits, right? So qubits are the most fundamental element in the quantum communication because they act as the carriers of quantum information. In classical computing, information is stored using the bits, and where each bit can exist only in one definite state at a time, either 0 or 1, right? And a qubit behaves very differently, and qubit is represented using a quantum state, which means before measurement it can exist in a combination of 0 and 1 simultaneously. So this property is called as superposition. And instead of storing the information in a fixed binary form, a qubit stores a probability amplitudes, right, associated with the different states. That is why quantum systems can process information in much richer state space compared to the classical systems. And one important point to understand is that qubit does not simply mean 0 and 1 at the same time it, in a classical sense. Rather than system exists in a probabilistically until observation happens. Okay, only during the measurements does the qubit collapse into a definite output state, right? Yes, another major reason qubit are important for cryptography is their sensitivity to observation. Like quantum states cannot be measured or copied without affecting the system itself, right? According to the no cloning theorem. And when an external party tries to intercept or observe the qubit during the transmission, the quantum state gets disturbed. So this disturbance changes the probability of distribution or collapses the state unexpectedly. So, as a result, the communicating parties can detect that interference has occurred. Okay, so this property becomes the foundation for eavesdropping detecting in the quantum cryptography. And qubits also supports entanglement, where multiple qubits become correlated with each other even when they are physically like separated, right? And this enables advanced communication protocols like quantum key distribution, teleportation protocols, as well as bb84 and superdense coding. Okay, so which will later implement in the demo section. Now, speaking about the quantum gates, once qubits are prepared, the next step is manipulating them in a controlled manner, right? So, this is achieved using the quantum gates, and quantum gates are the operation that transform the quantum states. In classical system, logic gates like AND, OR, and NOT manipulate binary bits. Similarly, quantum gates manipulate qubits, but instead of operating on a fixed binary bits, they operate on a probability amplitudes and quantum state vectors. Okay, so different quantum gates perform different transformations. For example, hadmat gate, right, it is widely used to create the superposition between the qubits, and when applied to a qubit, initially the state will be in 0, and it transforms the qubit into a balanced probability state, that is 0 and 1. But the Polis X gate behaves somewhat similar to the classical NOT operation, okay, by flipping the state. And Polis Z gate changes the phase of the quantum state. And then we have the multi-qubit gates like C NOT gate, that is control NOT gate, which are extremely important because they create entanglement between the qubits. So the entanglement is critical in quantum communication because it creates stronger quantum correlations required for secure protocols, right, to transfer the data. And these gates together allow us to encode information into qubits in the controlled as well as reversible way. And without the quantum gates, the qubits would simply remain unchanged, or no communication protocol could actually operate. So the quantum gates from the operation back is the it is the form of operational backbone of quantum cryptography. What and all things it will enable are, it will enable encoding, transformation, as well as entanglement creation and protocol execution. Okay. So after encoding information into the qubits, the next challenging is transmitting those quantum states from one party to another, right? So this is the role of the quantum channel. A quantum channel is the communication medium through which quantum states travel. Okay, unlike the classical communication, quantum transmission is extremely sensitive because quantum states are fragile and can easily lose their properties due to environmental interactions. So the channels therefore must preserve quantum coherence during the transmission. The quantum channel can use optical fibers or laser based for free space communication and satellite communication or dedicated quantum networking infrastructures. Okay, so the transmitted information is not directly visible like classical packets traveling over a network. Instead, the actual quantum state itself carries the encoded information. And one important aspect is that quantum channels help preserve properties like superposition, entanglement, while the qubits travel between the communicating parties. Okay, so one common misconception is that quantum cryptography works entirely using only quantum systems. In reality, classical communication still plays a very important role. So like quantum channels and classical channels works together in secure quantum communication systems. Okay, so the quantum channel handles the transmission of quantum states, while the classical communication channel is used for coordination and verifications. For example, after measurement, communicating parties often need to compare certain results and synchronize the operation or validate whether the transmission was successful or not, right? And these tasks are handled using the classical communication. And classical channels are also important for basis comparison, error checking, synchronization, and identifying possible eavesdropping attempts. So, in protocols like QKD, the like quantum key distribution, the actual key verification process depends heavily on classical communication after quantum transmission is completed. An important point is that classical channel itself does not carry the secure quantum information. Instead, it supports the communication workflow around the quantum process. So, the quantum cryptography is actually a hybrid communication architecture where quantum system provide a security through quantum mechanics, while classical system provide coordination and verification support. The final stage of communication process is measurement, right? So the measurement systems are responsible for observing and reading the received quantum states. So this steps is extremely important because quantum information behaves very differently before and after observation. Before measurement, the qubits exist in a probabilistic quantum state, but once measurement happens, the quantum state collapses into a definite classical outcome, such as 0 or 1. Okay, so this final stage device therefore acts as a bridge between the quantum world and the classical world. It converts the quantum information into a readable classical data that can be interpreted by the receiver. Okay, so the basis in which the qubit is measured also matters significantly. Measuring in a different basis can produce entirely different outcomes because the property probability amplitudes depends on the measurement orientation. And measurement system also contribute to security. If an attacker tries to intercept or measure the qubits during the transmission, that observation changes the original quantum state. So as a result, the receiver may observe the unexpected errors or disturbance during the final measurement. So this allows communicating parties to detect the possibility of unauthorized access or eavesdropping attempts. So measurement is not just about reading the information, it is also deeply connected to the security mechanism itself, okay, in the quantum communication. So now let us connect all the components together and understand the complete workflow of the quantum cryptography step by step. Okay, so the process begins with qubit preparation. So at this stage, qubits are initialized into a specific quantum state depending on the communication requirement. These states may be basis states or superposition or entangled states. And the second stage is encoding, and here the quantum gates are applied to manipulate the qubit states and embed the intended information. Okay, and different combination of gate transforms the probability amplitudes and the phase relationship of the qubits. So this is where the actual quantum information processing the happens. And in protocol like superdense coding, specific gate operations allow multiple classical bits to be represented using the entangled quantum systems. And after encoding, the qubits enter the transmission stage. And the encoded quantum states are sent through a quantum channel, such as optical fibers or free space communication. So during this stage, preserving the quantum properties becomes extremely important because environmental interactions can disturb the quantum states. So once the qubits reach the receiver side, the measurement stage begins, and the receiver performs the measurement in the required basis to extract the readable classical information from the quantum states. And this measurements collapses the quantum states and converts the probabilistic quantum information into a definite output values. And finally, the verification stage is performed using the classical communication channel. Both communicating the parties compare and validate certain results to ensure like successful transmission have happened, and synchronization and absence of eavesdropping or unexpected disturbance. So this entire workflow combines quantum states separation, quantum information encoding, secure transmission, and quantum measurement and classical verification together into one secure communication process. Okay, so these slides give you a more detailed technical view of the same workflow. So in this first stage, qubits are initialized into a carefully prepared quantum states. Okay, and this initial states determines how the information will later be represented and processed. And the second stage uses the quantum operations such as Hadmard, PolyX, PolyZ, and CNOT gates. And these operations manipulate the qubits mathematically by changing their amplitudes, phases, or correlations. And this allows the sender to securely encode the intended information into the classic quantum systems. And the third stage is transmission through the quantum channel. Okay, sorry. Yeah, the encoded qubit travel between the communicating parties while attempting to preserve fragile quantum properties like coherence and entanglement. And at the receiver side, the measurement device performs observation in a selected measurement basis, and the quantum state collapses into the classical outputs that can now be interpreted as a readable information. And finally, the classical communication channel performs a verification task such as error detection or synchronization and eavesdropping validation. So even though quantum mechanics handles the secure information transfer, classical systems still remain important for managing the communication workflow. So why qubit for data encoding, right? So one important question naturally comes here, right? So the first reason is superposition, and a classical bit can be represented only one definite value, right, at a time, either 0 or 1. But a qubit can exist in a probabilistic a combination of both states simultaneously. Like this creates a much larger representational space for information processing. And the second reason is high density encoding uh, capability. So because quantum states operate using probability, amplitudes, and state vectors, information can be encoded in a more efficient than in purely classical binary systems. Okay, The protocols like superdense coding are excellent examples of this concept. So, where entanglement allows a single transmitted qubit to effectively communicate two classical bits of information. And the third reason is security through the observation sensitivity. The quantum states are inherently sensitive to the measurement. Any attempt to the observe or intercept the qubit changes its state. So this makes unauthorized access detectable, which becomes a major advantage in the secure communication systems. And the fourth reason is the protocol support. And qubits naturally support advanced like quantum communication protocols like quantum teleportation, key distribution, and entanglement swapping, as well as the superdense codings. So these protocols rely on uniquely quantum properties that do not exist in the like classical communication systems. Like every technology, quantum cryptography also has both strengths and practical limitations. Okay, so one of its biggest advantage is security based on quantum physics itself, and instead of depending only on computational difficulty, the system uses the laws of quantum mechanics to protect the information. And another major advantage is eavesdropping detection. And since quantum state changes during the unauthorized observation, interception attempts can introduce detectable disturbance into the communication process. And quantum system also follow the no cloning principle, which is unknown quantum states cannot be copied perfectly. This prevents the attackers from secretly duplicating the transmitted quantum information. And quantum cryptography is also considered future resistant because it is designed to remain secure even in the presence of powerful quantum computers that may threaten many classical encryption methods. At the same time, there are important limitations, like quantum communication requires highly specialized hardware such as photon generators, quantum detectors, cryogenic systems, and stable transmission infrastructures. Right? So, maintaining this quantum coherence over long distance is also challenging because environmental noise can disturb the quantum states, and this currently limits large scale deployment, and the implementation cost is still very high compared to the conventional communication systems. And in addition, the overall setup and the maintenance process is technically complex because precise control. Okay, and so while quantum cryptography offers revolutionary security capabilities, large scale of practical adoption still depends on overcoming several engineering and technical challenges. And to practically implement quantum communication protocols, we need to develop we need a development platform that supports like quantum circuit design, simulator access, hardware execution, and a multi-framework programming, right? So this is where qBraid becomes very useful for us. So qBraid provides an integrated cloud-based quantum development environment that simplifies the process of building and testing quantum applications. And one major advantage is multi-SDK support. Okay, it allows developers and researchers to work with different quantum programming frameworks like Qubit, Pennyline, and optimization frameworks also. And this makes experimentation and learning much more flexible. So qBraid also provides access to simulators as well as real quantum hardware provider. This means users can first validate their quantum circuits using the simulators like high-end simulators from AWS, IonQ, as well as Quera, and later execute them on the actual quantum devices like Rigetti Anka 3, IQM Garnet, okay, and Quera, which has 256 qubits on actual quantum devices when required. And another important capability is simplified circuit execution. So instead of manually managing complex backend integration, qBraid streamlines the workflow for writing the circuits and selecting the devices and running the jobs and analyzing the results. So for academic and research environments, this becomes especially valuable because learners can focus more on the understanding the concepts and protocol behaviors rather than spending excessive effort on the infrastructure management. Okay, so the qBraid therefore acts as a practical bridge between the theoretical quantum communication concepts and real implementation of quantum physics. So once we have understood the theoretical foundation behind the quantum cryptography, right, like how qubits behave, how information is encoded, how transmission happens, and how security is achieved using the quantum mechanics. Now the focus shifts from the concept to the implementation part. In this live demonstration, we will practically build and execute a quantum communication protocol using the qBraid. So the demo will mainly focus on understanding how quantum circuits are used to encode information, manipulate qubit states, and create entanglement and recover the information through the measurements. Okay. So the objective of this demonstration is not only to run a quantum program, okay, but to understand the complete workflow behind the implementation of quantum communication protocol using the qBraid. During the demo, we will first see how qBraid allow us to access and inspect available quantum devices and simulators, and this helps us understand how quantum jobs are executed on the different computational backends. And sorry, and next we will build a quantum circuit step by step. Okay, so while constructing the circuit, we will analyze how qubits are initialized, how entanglement is created, and how information is encoded using the quantum gates, and how decoding happens at the receiver end. And we will also observe how measurements convert the final quantum states into a readable classical outputs. So another important objective is understanding the simulation and result interpretation. So overall, the demo is designed to provide you an practical exposure to quantum circuit development and executing the workflow and measurement analysis. So for implementing this demo, multiple tools and libraries work together as part of the quantum development workflow. The primary environment used here is qBraid Lab. Okay, so qBraid Lab provides the cloud-based workspace where we can write, execute, and manage the quantum programs directly from the browser. And to interact programmatically with devices and execution workflows, we use the qBraid SDK. And the SDK simplifies the backend management and helps connect our circuits to the simulators or supported hardware providers. And the quantum circuit itself will be developed using the Qiskit. And Qiskit provides the quantum programming framework required for qubit creation, gate operation, and circuit constructions, and as well as measurement implementation. And next tool is Python, which act as a overall programming language that integrates all these components together. Like we also use NumPy for handling the mathematical operations as well as array based computation required right during the analysis. And matplotlib, it is used for visualization of outputs such as probability distribution, histograms, and measurement result analysis. And together these tools are used to create a complete workflow for designing a quantum protocol and simulating execution, analyzing results, and understanding quantum communication behavior practically. Okay, so let's jump to the demo part now. Yeah. So once you have created the account and once you have logged in inside the qBraid platform, this will be your dashboard page. Okay. Here you will be having an access to check what are the devices available inside the platform. Like in total, we have 36 device access, out of which 25 are real QPUs and 11 are simulators. And in this 36, we have 18 online devices available now. And if you want to check the device specification, you can just click on the device and click on view details. You'll get all the details like name of the device, who is the provider, and the type of the modality, and like how many qubits are available inside that device. Okay, So to run inside the simulator or the hardware, we need to have the credit points. Okay, so this is what we call as a credit, which will act like a voucher to redeem the details. If you need more information about this, you can just go through the webinar one. Okay, we have given an full demonstration regarding the account creation till the how we are going to use the credits. Okay, so first, if you when we are going to create our new projects, first we need to launch the server. Okay, so your programs, everything will be launched on the server itself, so don't need to worry about your like RAM process of your computers. Okay, so let the environment get loaded. Okay, so here this is the environment. It is just similar to the Jupyter notebook, and it follows the same file system. You can just go here, create new folders, and the files inside that in the IPYNB format. Okay, and if you want to check what are the devices available, you can check it here also. And your job status, you can check it here. For environment creation, you don't need to go for programming method. You can just click here and you can create environment by adding the libraries here. Okay, so before starting the code, let's first understand what exactly we are trying to achieve through this program. Okay, so the goal of this implementation is to simulate a secure quantum communication protocol called as super dense coding. So, in normal classical communication, if Alice wants to send 2 bits of information to the Bob, she needs to physically send 2 bits, right? So, but in super dense coding, we try to achieve something very different. Like using entanglement, Alice will only send 1 qubit, but Bob will still be able to recover 2 classical bits of information. So, through this program, we are trying to practically understand how entanglement is created, how information is encoded into a qubit, and how gates modify the qubits, and how the receiver interprets the qubits, and how the simulator handles the entanglement and verifies whether the communication differs from classical communication. Okay, so the simulator helps us visualize and verify whether the communication differs or not. So by the end of this, sorry, just a minute. Yeah, sorry for the inconvenience. Yeah, let me resume it. Yeah. So another important thing is like we are not directly seeing the quantum states physically. So the simulators helps us visualize and verify whether the communication worked correctly or not. Okay. So by the end of this implementation, we should clearly understand why entanglement is important and how quantum communication differs from classical communication, and how one transmitted qubits can effectively carry 2 classical bits when entanglements are already shared. Okay, so in the first step we are going to import the numpy. Why? Because now in this particular program numpy is mainly included because quantum computing application often involve handling arrays, probabilities, and mathematical operations. Even though we are not heavily using NumPy here, it is commonly imported as part of quantum programming workflows. And next we import the matplotlib. So now why we are importing this? Because later in the program we want to visualize the result instead of only printing the output as a text. Grabs help us clearly see, right? So which message was received and how many times it appeared, and whether the protocol is working consistently. So matplotlib helps convert the measurement results into from Qiskit, we import the quantum circuit. The quantum circuit is basically the workflow. And inside the circuit, you can think of it like creating a complete path of an AER that gives access to running quantum programs on actual quantum noisy, right? So instead of using the real hardware, we use the simulator. So the simulator behaves like a virtual quantum computer and help us test the protocol safely. And this function like helps display the final outputs as the histogram, that is Qiskit dot visualization. And why do we need that? Because quantum programs are usually executed many times, right? And instead of getting only one output, we get output distributions. And histograms help us analyze whether the communication behaved correctly or not. And next we have the backend. So now we select the simulator backend. This step is basically telling the program where should this quantum circuit run, or here we are choosing the AER simulator. So the entire communication protocol will run inside this simulated quantum environment. Okay. And next, this printing line, this line is just confirming that simulator is ready or not. Okay. So the output is showing like backend is ready, like meaning the environment is successfully prepared and ready to execute the quantum circuits. Next step. So now the actual quantum communication setup starts. Like before Alice sends any message, both Alice and Bob must already share the entanglement, right? So this shared entangled pair is the main resource that makes superdense coding possible. And here we create a circuit using two qubits, and one qubit belongs to Alice and the another belongs to the Bob. Initially, both qubits starts in their default state. At this stage, no communication has happened and no entanglement is exist, and both qubits behave independently. Now we apply the HUDMAT gate, okay, to get the first qubit. Why we are doing this? Because we want the qubit to start behaving quantum mechanically instead of classically. So the Hadamard gate creates the superposition, meaning like the qubit is no longer logged into only one fixed values. So this prepares the qubit for entanglement creation. Okay, and now we apply the C naught gate, right? So this is the step that creates the entanglement. What are we trying to do? Sorry, excuse. Yeah, sorry. So yeah, now we apply the C naught gate. This is the step that creates entanglement. Okay. So what are we trying to achieve here? We want both qubits to become the connected, right? Like entanglement. So instead of behaving like two separated independent qubits, they now behave like one correlated quantum system. And this shared entanglement is what later allows Alice to send two bits using the only one circuit. The output visually shows the operation we performed. And first we see H gate, right? So creating the superposition, and then we see the connection created by the C NOT gate. So this output confirms that the Bell pair preparation stage is complete. And yeah, so now the entangled pair is ready, right? And Alice now wants to send an information to the Bob. The interesting thing is Alice wants to send two classical bits. Okay, the possible messages are 00, 01, 10, and 11. And instead of sending two separate classical bits, Alice modifies her qubits using the quantum gates. Like this function handles the define Alice code, right? So this function handles the encoding process. Depending on the message, like different gates will be applied to the Alice qubit. And next, this qc dot barrier. So this barrier is only for the visualization. It separates the encoding section in the circuit diagram, and it does not affect the communication itself. And if message is equals to 00, pass, right? It means Alice does nothing and the entangled state remains unchanged. Next is if Alice wants to send 01, she applies the X gate. Why? Because the X gate changes the qubit state. So by applying this gate, Alice modifies the shared entangled system in a specific way the Bob can later recognize. Okay, and this QC dot Z of 0 for message 110, Alice applies the Z gate. Why? Because this gate changes the internal behavior of the quantum system, quantum state differently from the X gate. So now the shared entangled state carries a different message. Okay, and for message 11, like QC dot 0 Z of 0 and QC dot X of 0, for message 11, both Z and X gates are applied together. So this creates another unique encoded state. So every message corresponds to a different modification of the shared entangled qubits. And now when we print the circuit, we can visually observe the where the encoding operation happens, right? For example, if the message is 10, we see the Z gate appear in the encoding section. So the circuit diagram helps us visually track how the message is being encoded. Next, after encoding, after encoding, Alice sends her qubit to the Bob. And now Bob has original qubit plus Alice transmitted qubit, right? And his goal is to recover the original message. And this define function performs the Bob's decoding operation. And next, QC of 0, comma 1. Why are we doing this? First, Bob applies the C naught gate because Bob now needs to reverse the entanglement structure and start extracting the encoded information. Okay, and next it applies the HUDMAT gate. Why? Finally, the measurement like this helps convert the encoded information into the form of that can later be measured and interpreted classically. And finally, the measurement happens, right? So this is the step where the quantum states like system gives us readable outputs. Okay, after measurement, the final classical bits become an available. Now if we observe the full circuit carefully, okay, so the left side creates the entanglement, right? And the middle section performs the encoding and the right side performs the decoding and measurement. So this full circuit now represent the complete communication process from sender to the receiver. And now instead of testing only one message, we automate the complete workflow. Okay, so this define function, right? This function combines all the steps together like bell pair creation, encoding, decoding, execution, and result collection. Okay, and the number of shots is 1024, that is nothing but the probability. And now this is important, why? Because quantum systems are probabilistic. So instead of running the circuit once, we run it many times. Okay, and each execution is called as shot. Running multiple shots helps verify whether the protocol behaves consistently or not. And next is result part. This line actually executes the quantum circuit on the simulator. Okay, so that output, what it will tell us is, now we collect the measurement outputs and it will tell us like what outputs appeared and how many times each output occurred. Okay, and next is understanding the output. Now let's understand the outputs carefully. Like, we can see sent is 00 and received is also 00, and sent, whatever data have been sent, that is 01, but received is 10. And sometimes it is like sent 10 as well as received 01, and sent 11, received 11. Now many people get confused here, why are like 01 and 10 appearing swapped, right? So this happens because Qiskit displays measured bits in the reverse order during measure all. Okay, so the protocol is actually working correctly internally. And the most important thing here is the Alice transmitted only one qubit, but Bob successfully recovered two classical bits. And this becomes possible because entanglement was created shared beforehand. And now we visualize the output using the histogram. Okay, so this ax dot bar, this will create the bar graph. And next is, each graph represents one message. Okay, the x-axis shows the received output and the y-axis showed how many times the output appeared. And now notice something different, important, that is, for every message one output dominates strongly, meaning this protocol is consistently decoding the correct messages. Okay, and now we print the circuit for all the four messages. Okay, so this helps us visually compare the encoding process. For 00, no encoding gate appears, and 01, X gate appears, and for 10, Z gate appears, and for 11, both X and Z gate appears, right? So even though the like changes are small, internally the communication behavior changes completely. Okay, so now we perform one final verification step. Okay, so here, like, now we can increase the number of execution to 10,000. Okay, so this helps us to verify whether the protocol remains stable even after repeated execution. Now we can see every message achieves 100% accuracy, right? So like the communication worked executely, it means like the communication worked correctly and the decoding was successful and no incorrect outputs are appeared. Okay, so now this perfect accuracy happens because we are using an ideal simulator. Real quantum hardware usually contains noise as well as environmental disturbance and hardware what imperfections. So real hardware results may not always look this perfect, like it will have it, simulators will have a perfect ratios. And final conclusion, what I want to say this, like, so with this we successfully implement the complete superdense coding protocol using the qBraid and Qiskit framework. Through this implementation we understand how entanglement is created and how information is encoded into qubits and how quantum gates modify communication states and how decoding happens and how measurements recover the information. And the biggest takeaway from this entire implementation is this, like, classically sending 2 bits requires transmitting 2 bits, but using superdense coding, because entanglement is already shared, 2 classical bits can be communicated using only one transmitted qubit. Okay, and this is one of the major advantage of the communication systems. Okay, so that concludes the demo session and we can jump to the Q&A session. If you have any queries, you can just drop it in the Q&A chat. Yes. So, like, if you encode an information in a qubits, can't we use entanglement property to communicate rather than classical communications? Yeah, that's what we demonstrated now, right? We created an entanglement between two qubits and we shared the information without sharing the actual data, like using the actual communication setup. You can use it in a two different way. One, you can use classical communication setup, or you can use the entanglement process. And what is the advantage of using qBraid when compared to IBM Qiskit? Max Rajeshwari ma'am, how many qubits can be simulated in this platform? Okay. So the major advantage you get by using the qBraid is that you will not get only access to uh, what you'll say IBM computers. When you are using the IBM Qiskit, you will get only access to the IBM computer only, right? But here, if you don't have the account on different cloud platforms also, like for AWS, if you want to use the AWS simulators like SV1, State Vector 1 simulator, or TN1 and all, you can just log into the qBraid platform. If you have the license, you can just get access to multiple, as I said, 30 simulators, as well as sorry, 30 is the total device, but you will get access to all the device like simulators as well as quantum computers. Okay, so that is one of the major advantage. And if you are using the IBM Qiskit, you will get to use only the Qiskit platforms. Okay, like Qiskit framework, but here you can use multiple framework for multiple purpose, like Qiskit framework, Circ framework, as well as Pennyline for machine learning models also, right? Okay, so Krishna Prasad sir, some basic doubts. What is measurement means? Same as decoding in classical transmission. Okay, so measurement means like we know that in qubits it appears in both 0 and 1 state, right? But when we are reading the outputs, we need an actual value, actual probabilistic value. Sorry, we don't need a probabilistic value, we need the perfect ratio value, right? For that we will be doing the measurement here. So this measurement comes from the double slit theorem. Okay, so where your double slit wave will be actually acting like a single particle when an observer observes that wave particle. Okay, so that is what we mean as measurement. We need to do it. Why? Because qubits will be giving, if you don't do the measurement, you will be having an probabilistic value. It can be either 1 or 0, but if you want an actual value, you need to do the measurement in the quantum. Yes, actually, verification is same. Like, why? Because we will be doing this verification whether the data, whatever, like we saw in the demonstration, right? What are the things Bob received, right? So Bob received the actual value which shared by the Alice or not. We need to do that verification step. That is what verification means in this quantum secure transmission protocol setup. And can we use the quantum communication to transmit public data securely? Yes, we can use the quantum communication setup for transmitting the public data securely. Yes, compare superdense coding with quantum teleportation. What resources are consumed in each protocol? What is transmitted physically and logically? Right. So in quantum teleportation, you know that we will be not sharing the actual data. We will be sharing the qubit states, right? But in superdense coding, we are sharing the classical bits. What we are trying to show in superdense coding is like two classical bits can be shared using the single qubit. That is what we are trying to achieve here. And next we have Kavita ma'am. How to differentiate between the eavesdropping and noise on the measurement at receiver end. Right. So here, like on the basis part. Okay, so whenever Bob is working on the basis part, right, like applying the different logic gates, that time he will be not getting the actual value what he was expecting from the Alice. Okay, so that time we can see that eavesdropping have achieved. Noise will be like, it is, you can see, for example, I wanted only 00 and 11 state, but I got some different state at less number of probability. That is where the, what you say, noise comes from the hardware. Okay, and why is the HUDMAT gate necessary before the CNOT gate in the Bell state generation? Ratio Chaudhary sir. So why we need HUDMAT gate is like, we need to apply, like we need a qubit in the superposition state to create the entanglement state. Okay, so that's why we need HUDMAT gate to be implemented on qubit to create an superposition. Okay, and how to get credits? Is it licensed? Yes, Kavita ma'am. Like you need to get the credits by purchasing the license. Like if you need any support from this, like Digitoad is here to help. You can contact the Digitoad support and explain how qBraid handles circuit transpilation between the gate sets. Okay, so like this happens at the back end of the qBraid, like it has a transpiler. Okay, so the back end work is like it will like it will convert the whatever circuit, like you have built it using the Qiskit or circ framework. You can just like build it using the whatever known framework you have. You can build that circuit and you can just deploy it, and the transpiler at the backend will help you to convert this actual framework, like circuit, into a like that hardware understandable format. Any other questions? Yeah. Okay, I guess that answers everyone's questions. And thank you once again for everyone for participating in the webinar, and have a great day. Thank you.